Building an omni-channel notification platform means engineering a system capable of processing and delivering millions of messages every single day across email, SMS, and push notification channels. The common, naive approach is to treat these outbound messages as simple synchronous API requests. A user takes an action, and the core application directly pings an external provider like Twilio or SendGrid, waiting for a success code. The flaw in this logic appears the moment that external provider experiences high latency. The internal server sits idle, holding open connections waiting for a response, until it triggers a timeout, exhausts its threads, and cascades a crash back to the core application. A notification is essentially just a small JSON payload, yet tying its delivery directly to the lifecycle of an internal application introduces massive vulnerabilities. Network partitions, provider throttling, and silent data divergence are guaranteed to happen at scale. Relying on synchronous safety means a downstreaming telecom hiccup can take down your checkout page. Guaranteeing high deliverability requires abandoning this direct link. The architecture must become asynchronous and decoupled, completely insulating your internal business state from the chaos of the external internet. The decoupling process begins at the ingestion boundary. When a user completes a purchase, the system must write that order to the database and simultaneously publish a receipt notification to a message broker. A standard dual write approach fails here. If the database commits but the network drops, the user is charged but the receipt is lost. To guarantee atomicity, the transactional outbox pattern simultaneously writes the business state and inserts the payload into a dedicated outbox table. Because both inserts happen within the boundaries of a single atomic local transaction, they are strictly bound. If the outbox write fails, the entire transaction rolls back, preventing any silent data loss. To move secured records to the broker, a relay process takes over. This independent worker runs detached from the main API thread, grabbing outbox rows and pushing them to the broker. This relay can be configured to tail the database transaction log directly for sub-millisecond latency, or it can rely on standard database polling for a simpler, highly portable architecture. When scaling horizontally, multiple workers attempt to read the outbox at once. Applying row-level locking instructs concurrent workers to skip locked records, eliminating race conditions. By confining the ingestion failure domain to a single local database transaction, the system guarantees that no business action can occur without its corresponding notification payload being safely persisted for delivery. Once the message broker receives that safely stored payload, it forwards it to the internal notification service layer. Here, the unified stream is divided into distinct, isolated message queues dedicated specifically to email, SMS, and push. Without this separation, a massive batch of low-priority traffic causes head-of-line blocking, trapping time-sensitive alerts. Priority-aware routing prevents this. A marketing fan-out is sent down a low-priority path, ensuring a critical SMS bypasses the bulk traffic entirely. Before any message officially enters its queue, the service executes a final validation pass. It verifies user opt-out preferences and applies daily rate limits to ensure compliance. Strict queue isolation ensures that a localized provider outage or a massive marketing spike cannot cascade across the system and compromise critical alert timelines. At the edge of the system, fleets of stateless workers pull payloads from these isolated queues and transmit them to external providers. Every provider operates with specific validation quirks. Firebase, for example, will silently expire a device registration token if an application remains inactive for 270 days. When a worker attempts to send a message to one of these expired tokens, FCM returns an unregistered error. The worker must catch this exception and proactively delete the stale token from your database to prevent phantom delivery metrics. High-volume email delivery presents a far more severe constraint. Mailbox providers ruthlessly track your sender reputation based on your bounce rate. Amazon SES enforces hard limits. If your bounce rate hits 10%, AWS instantly suspends your sending privileges. To automate protection, a suppression loop routes that permanent bounce event directly to a backend service, which flags the address in a global suppression list. Any future dispatch attempts to that known bad address are blocked immediately at the ingestion boundary, protecting your sender standing. Because external providers operate as hostile environments with strict enforcement rules, the architecture relies on these automated internal cleanup mechanisms to survive. The system must also track precise delivery status transitions, such as queued, marked as sent, and ultimately delivered, using asynchronous callback webhooks from providers. This creates a massive ingress challenge. Dispatching 10 million SMS messages can easily generate 20 million incoming status webhooks in a highly compressed timeframe. Routing this sudden volume of inbound requests directly into a traditional database will overwhelm the connection pool, causing catastrophic write locking and collapsing the system. To insulate the database, status callback endpoints are deployed as serverless functions. They ingest the massive payload volume without managing fixed connection pools, dumping the data directly into a high-throughput streaming system like Kafka or AWS Kinesis. This stream buffers the webhook data, allowing backend services to read and process the status updates asynchronously in controlled batches. To safely monitor a high-throughput outbound system, the inbound monitoring infrastructure must be equally decoupled, preventing a sudden spike in observability data from causing a core database outage. Tracing the complete architecture from the local database outbox through the message broker into isolated queues, out via stateless workers, and back through the serverless webhook stream, the failure domains are strictly contained. This structural decoupling provides one core guarantee, at least once delivery. Because the system relies on network retries to survive transient failures, messages may occasionally be queued and processed multiple times. The architecture is designed to handle this safely. The design sacrifices immediate, synchronous delivery confirmation. In exchange, it achieves eventual consistency and infinite horizontal scalability. A bulletproof notification platform does not assume external providers will succeed. It assumes they will fail, throttle, and rate limit. It uses internal buffers and asynchronous processing to guarantee the message always survives.